Do you have any other questions about previous lectures? Mm. Okay, so today we're going to study the wave equation. In 1+1 dimensions. So this equation is the following. And if you introduce new variables, xi, which is t plus x, and eta, which is t minus x, then this equation can be written as u xi equals to 0. Or maybe better to have the full change of coordinates between eta and xi. In a sense, it's better to have expressions for derivatives in xi and d eta. So I want to write it like this. Or maybe make it the other way around. On the question, the audience, what coefficients should I put here and there? Yes, yes. Because when you try to check the action of the derivative on eta and xi, you see that the xi of eta is 0 as it should be, but the xi of xi has two terms, dt of t and dx of x. So it's 1/2 plus 1/2. So there is the following change of coordinates. Oh, by the way, let me consider this equation already on the right hand side. So let me put here some f of t and x. So in this way we see that these coefficients are important. So if I write this equation using index sign and eta, we see that it is written as u xi eta equals to f of 4 times u xi eta equals to f of tx. So this is this equation in new coordinates. And but first, let us consider the case when f is 0, and ask what kind of problems we can solve. So. So and we discussed it last time, and so the question is, who remembers how a solution of this equation looks like in this case? Mm-hmm. Yes. And so it is f of mm, uh, t plus x plus g of t minus x. Mm. And uh, so it's a general solution of the homogeneous equation. And well, any questions on this? Mm. Yeah, let us now ask what specific problems about this equation we want to solve. So this equation comes from some wave phenomena. For example, it can describe mm, mm, propagation of waves in a string or in or in some medium. So suppose that we have some string, and suppose that it is infinite. So uh, so to describe the motion of the string, we need to fix its initial position, and also since it is described by second Newton's law, we should also give velocities of all points of the string. So the physically motivated problem, so it goes from minus infinity to plus infinity. And this is a mm, this is our initial string. So the physically motivated initial problem for this equation is the following. Mm. We need to fix u of 0 x equals to 0 of x uh, ut of 0x equals to some u1 of x. No, x is coordinate. So, yes, so on this picture, uh, here is x, here is u. So, uh, so, so if we draw it in the tx plane, it will look in the following way. We have some uh, boundary at t equals to 0. And we fix here u of 0, 0 and x, and so equals u0 of x, and ut of 0 and x equals to u1 of x. So we fix two derivatives of this function, and then we need to find u of t and x inside. So it's described by the wave equation. We need to express u of t and x in terms of u0 and u1. So, and let us solve this problem. So we know that if some function satisfies the wave equation, it can be written as a combination of functions of t plus x and t minus x. And we simply need to adjust this formula to these boundary conditions. So, so we can write that u0 of x equals to what? F. Oh, sorry. Actually, I'm always missing this thing, and so that it is better to write not t minus x but x minus t, because otherwise, sorry, uh, I will change it now. X minus t, x minus t, and here it's minus. Sorry. So this u0 of x will be f of x plus g of x. And when we differentiate these two functions in t and put t equals to 0, then what we will have for u1 of x? Hmm? Yes? Yes. Thanks. So we have something like this, and it's inconvenient to work with this first derivatives, so we can integrate this equation to get something like this. F of x minus g of x equals to some constant plus integral, for example, from 0 to x, u1 of y d dy. So now when we have these two equations for sum and for difference of f and g, we can simply take some of them. Hmm? But where is time? Yeah, but what do you mean by time? They are just functions of a single variable. And this variable is x plus t and x minus t. We differentiate them in time, which enters these variables, and then put time equal to 0. So it's derivative with respect to the only argument of this function. So, so now we can take some of these two equations to get to fx equals to uh, u0 of x plus c plus go from 0 to x u1 of y dy and a difference to g of x equals to 0 of x minus c minus integral from 0 to x of y 1 of y dy. Now we can take these two functions. Of course, we need to divide the right hand side by 2 and yes, substitute them into the formula for a solution. Well, the good thing is that this constant cancels, and here we have sum of two integrals. Well, represent difference of two integrals. One integral is from 0 to t plus x minus integral from 0 to t minus x 1/2 of 2 of ty dy. Which can further be written as u0 of t of x plus t. Oh, sorry, not t minus x, but x minus t. So it's a formula that expresses a solution of this equation in terms of initial conditions. So, are there any questions about this? So, and let us see how this formula works. Suppose that u u1 of x equals to 0. And u0 of x is given by the following picture. So let this be maybe 2. and this is -1 plus 1. So in the initial condition, so it is some string that has this shape. So if you apply this formula, then the second term simply is not there. But and the first term is an average between two functions, shifted by t in positive direction, shifted by t in negative direction. So it can be drawn in the following way. So u0 of t and x is is sum of two uh, functions. So s time t, and here the one half of this function, and this is 1 plus t, and this is 1 minus t, and this is u of x minus t. Plus another function shifted in the opposite direction. This is u of x plus t, one half. So if we try to turn this into a movie, then it looks like this. So, so first, let's see what happens in the middle. We have a sum of two functions with opposite slopes. So the slope of a resultant function is 0. So we will have some flat a flat shape, and value of this function will equal to 2 minus 2t. Oh, sorry, 2 minus 2t, or yes, I think yes. So then we see these 2 points when the slope changes. It will be 1 plus t and 1 minus t. Oh, no, sorry, it is t n minus t. T n minus t. And here we have 1 plus t and 1 minus t. So then this function evolves further. Oh, sorry, no, I made some mistake here. Mm, no, uh, there is a further change of this slope at the end. Mm, so. Mm, Let us better draw it for some values of time, not for generic time. Mm, mm, maybe maybe it's fine. So t equals 1/2 should be enough probably. Or maybe sorry, maybe better to mm, take 1/4 to see this phenomenon. Oh, sorry. So uh, there is this flat region between uh, -1/4 and 1/4. maybe better to draw it here. Mm, there is a region of with double slope, and then the region with uh, with ordinary slope as before. So it'll be something like this. Yeah. So. And then when t equals 1/2, this two shapes start disconnecting. So when t equals 1/2, we'll already see this picture 1/2 minus 1/2. Then they disconnect even further. So it looks this way. Mm. So this is 18 greater than 1/2. And then at some point we see this picture. So what is the value of time when we see this? What what do you think? Mm-hmm. Yes. And this value is 1. Oh, and then of course they move in opposite directions. So this one moves to the right, and this one moves to the left. So there are two waves that were interfering originally, but then they simply go in opposite directions. Mm. Well, are there any questions about this picture? Mm. And if you draw this on the ATX plane, if you track positions of this discontinuities in the first derivative, then this picture will look like this. Uh, and this is x, and this is t. So we have uh, two lines, x equals t and x equals minus t. Mm, and there are these two maxima that go in different directions with the speed of light or of sound. So these lines are called characteristics. So waves travel according to these characteristics. Mm. So, mm, so far we solved this problem with initial conditions. By the way, let us look at one more example uh, of what happens if we consider the opposite situation. Uh, when initial value is zero and the initial derivative is something. Well, let us see what happens when u of u 0 of x equals to 0. Ut of x well, u1 not u1 of x equals to this. Let me think what I want to do precisely. So again, this is from -1. This is uh, this is 1. This is 1. This is -1. So let us say integrate this u1 of x, and we can integrate it from minus infinity for simplicity. So we go integral from minus infinity to x u1 of y dy, and it will have the same form as this function. And maybe we can put here -2 and -2 and 2 to simplify computations. So is it clear that it has this shape? So when we want to draw u of t and x, right there, it is u of t and x. Now it will be difference of on these two functions. So there will be some maybe better to write it not as a difference, but as a sum of function and inverted function. And yeah. Yes, I think like this. Let me check. Yes. When you skip, if you skip this initial stage, then at the end we get this picture. Two reversed waves traveling in opposite directions. So, and of course we can combine both initial conditions. Mm, it's clear from this formula, for example. Mm, if you uh, take a initial condition that is a combination of this one and this one, in a sense, we take u1 equal to this and u0 equal to this, then one of these two waves traveling to the right will be cancelled. And uh, we'll actually use this cake at some point. So, are there any questions on this? So, and uh, and now let us try to turn on non-trivial right-hand side of this equation. Uh, so originally we solved this initial value problem with zero right-hand side. But now we can switch to some non-trivial right-hand side. So utt minus uxx equals to f of t and x. Mm. U of 0 and x equals u0 of x. Ut of 0 and x equals to u1 of x. Mm. So, and now, since this equation is linear, we can separate initial value problem and problem with a non-trivial right-hand side. Mm. I can probably erase this picture because they're not very useful. So I generally study this problem with non-trivial right-hand side, with non-trivial U0, with non-trivial U1. But in principle, we can consider or we can consider three auxiliary problems. So let us take first problem to be this one. And this other function will be 0. It's one problem. Oh, sorry. This is 0. And the third problem. So suppose we know how to solve all these three problems. So how would you suggest me to construct a solution of the original problem? Yes. Yes. Well, this is possible because we are studying uh, linear equations. And we already see this phenomenon for this problem with initial conditions, that it depends on U0 and U1 separately. So since we know how to solve these two problems, we can concentrate just on this one. So we will study this. And to study it, we can use this change of coordinates. So our equation becomes u of eta xi equals to minus 1/4 f of t and x. So maybe at this point it is better to express t and x in terms of eta and xi. So t is xi minus eta over 2. Xi minus eta over 2. X is xi plus eta over 2. And when we see this, we can simply try to integrate on this. So let us integrate it once. So u xi will be some of a function that can in principle depend on xi. Phi of maybe c of xi plus integral from from something, and we need to decide well, the domain of integration for this function. Let us write some xi, some eta 0 of xi minus 1/4 d. Let us use some different name for this eta prime, d eta prime. So we just integrated this once, integral to xi. And then we can integrate this result of integration. Maybe we can denote this function c c prime. So another integration gives u equals to c plus of psi plus some other function c minus of eta.
I don't understand why we are integrating to C.
Sorry, because I made a mistake. Yes, thanks. So this other integral will be in some domain psi 0 to psi xi prime.
What's the subscript on the C?
Which one?
The one where you're pointing.
Plus. So we see here some functions that depend on eta and xi, which are solutions of the homogeneous equation. But we actually don't care about such functions because they can be taken into account in these problems. And the only thing we really care about is how to choose the domain of integration. And let us think about this. Maybe it's better to draw some pictures. So let me go to this blackboard. Maybe. So we have our original t and x plane. t and x. And we have the 45-degree rotation to pass to eta and psi. So uh, when uh, both x and t increase, we see that eta is constant and psi is increasing. So the psi axis is pointed in it's pointing in this direction. And when t decreases and x decreases, then eta also increases. So eta axis is pointing in this direction. So, and if you want to integrate some function from uh, so we see that upper domain of integration in this integral are given by psi and eta, and their domains of integration xi prime and eta prime. So the contributions to this function at point xi and eta come from this from this domain that ends like this. So the only question is how to draw it properly, because here we can draw upper domains of integration, but in principle there are some lower domains. And a very natural suggestion is to say that these lower domains are actually minus, are actually just minus infinities. So draw like this. So integration domain in eta and psi. So we can simply write that these two functions can be neglected, and this integral goes from minus infinity to psi, and oh, sorry, let me think. It's not about probably it's yeah. Oh, sorry. What did I draw? I Sorry, I swapped the two axes and no. Um, sorry. Let me just redraw this picture again. It was a mistake. So again, when t and x both grow, then we have x-axis. When t decays and x grows, then we have this axis, eta. Yes, directed like this. But we still want to have this integration domain because if you choose this, uh, maybe let me draw it on a separate picture. Well, we want to have this integration domain because in this way we can guarantee that when t goes to 0, the solution will equal to 0. Because we are studying this equation only in the upper half plane. We are studying it for the positive t. So, because when t goes to 0, we have this picture. Have a point on this line and this integration domain. Another option could be to choose this integration domain, for example, like this, or uh, any other variations with different lower value. Looking at this picture, we see that this domain corresponds to xi going to minus infinity and eta going to plus infinity. So, so this line is this line is xi going to minus infinity. This is eta going to plus infinity. So let us now use. By the way, shall we make some break? Or okay. Hmm? Mhm. So, okay. Okay, so we are studying in the integration domain in variables psi prime and eta prime. So the point inside this domain is described by psi prime eta prime, and this point is psi and eta. Going to this integral, we can make these choices of psi 0 and eta 0 of our integration domains. We can simply say that psi 0 is plus infinity and eta 0 is minus infinity. Uh, so probably did I? Yeah. So this is minus 1/4 integral from minus infinity to psi dx psi prime, integral from plus infinity to eta d eta prime f of psi prime minus eta prime uh, over 2 psi prime plus eta prime over 2. So in principle, it is some kind of answer, but we would prefer to have it in the original coordinates, since in t and x coordinates. Sorry, I forgot that. I know, not yet. So we see that this integral will have a negative sign because we are integrating from plus infinity to eta. So it's better to write it as an integral.
Constant 0?
Hmm?
Why the constant 0?
Which
Constant.
because if we choose integration domain in this way, so if we integrate from minus infinity to sine, not from a plus infinity, not from this direction, then when we send t to 0, we simply have nothing to integrate, and this function will vanish. So if we choose this integration domain, then we are sure that these initial conditions are satisfied. So and this is always like this. We need to make some choices about integration domains to satisfy the simplest possible initial or boundary condition. So. Can write it as 1/4 minus infinity to psi d psi prime integral from eta to plus infinity uh, d eta. Sorry, it's d psi prime. Now we have positive sign, but we would like to write this integral as an integral in a x t plane. So, um, and this domain is drawn here. So, integration domain in t prime starts, in principle, it can start from minus infinity, but since we are studying this equation for positive t's, we can restrict this integration domain by 0. From 0 uh, to t dt prime 0, or in principle it can be minus infinity. Let us put a 0. And question is, what is the integration domain for x? What are the upper and the lower uh, limits in that integral? How to describe this two lines? If you know that this is t, this is some point x. Maybe let me draw this picture here. And those are integration variables. We want to describe this domain. So when t prime equals to t, what are the limits of the second integral? Yes. So and then this point starts splitting, and it turns into this interval, and to this integral, into this interval. So let us say that it is some t1. This is t2. So
X minus t minus one.
x minus t minus t prime. Yeah, well, plus, and this one is, so in this case it is t, yeah, and this is x minus t minus t prime. Yes. So minus some negative, minus some positive number plus some positive number. Dx prime. Oh, and in principle, we have changed integration measure. Originally, it was dxi prime d eta prime, and so we need to write the Jacobian d xi prime eta prime over d d t prime x prime f of t prime x prime. So, and this Jacobian let's compute it. So, I will not care about science, but it is something like this. It will be 2. Or it can be checked in some other way. So, do you know what differential forms are? Probably not yet. I mean, then it won't be helpful. We can simply compute this determinant. So we see that the determinant is 2. So the integral itself is 1/2 times the integral from 0 to t dt prime, integral from x minus t minus t prime x plus so it was one way to describe uh, to describe this answer. We can also write it in some different way, because here we first integrate in t, but we could also integrate in we could first integrate in x. So let's try to describe the same answer in a different way. This is x prime, t prime. So if you integrate in x, then this integral will not be restricted in any way. Or we can say that, well, in principle, we can restrict it by these 2 points, or we can simply say that the right hand side is 0 for negative times. So this point is t, and this point is x. And this is x plus t, this is x minus t. So this is already the answer, but it can be rewritten. It, so this can be chosen as plus or minus and plus infinity. So equivalently here we could put minus infinity. Uh, dx prime. And what do you think about the time integration? What is its domain? Dt prime. Yes, in principle it can also be. Hmm? Uh, so mm, so it is t minus absolute value, right? Yes. Thanks. So there is an equivalent representation of the same integral, uh, f of t prime x prime. Mm. So this integral is uh, slightly better because computationally, of course, this integral is simpler, but from conceptual point of view, this one looks more similar to higher dimensional answers because in that case it's unclear what is x plus t minus t prime and x minus t minus t prime. But if we have absolute value, then it could in principle be generalized to a difference, to absolute value of mm, to distance between x and x prime, but of course this formula does not work in higher dimension. We have some other formulas that share some properties of this formula with expressions like this, but they are different. Mm. So uh, all this mm, all these expressions reflect the fact that as wave equation uh, mm, uh, i- i- the behavior of this wave equation is restricted by causality, in a sense that the only points, both in the right hand side or in the initial conditions that affect solution at point tx, are those from which the wave can reach our point of interest uh, moving with the speed of light. So we see that in points that lie outside this light cone cannot affect the value of solution at this point t and x. So. Mm. So if you want to write the full solution of this equation on the real line with initial conditions and the right hand side, we can simply take sum of that formula and this formula. It's also clear that this solution satisfies the initial conditions because when well maybe it's maybe the simplest way to see it is to look at this formula. When t is 0, then even this integral from 0 to t shrinks to 0. So this solution will be 0. And we can also check that its first derivative is 0 as well, because the area of this triangle grows quadratically with t when t goes to 0. So its first derivative in time is also 0. So are there any questions about this? Good. So uh, let us now uh, uh, go to a slightly more complicated situation when we have non-trivial boundary conditions. Mm, Probably I can erase this blackboard. So we started from this problem when uh, our function was defined on the whole real line. Uh, and it looked like some boundary in the Tx domain. And when you look at this picture, it's natural to ask what happens if you consider some different boundaries in this Tx plane. For example, what happens if you consider a boundary of this shape? And ask the same question. Mm, So let me erase everything. So these initial conditions are the same, and for boundary conditions, again, we need some extra motivation that could come from physics. And motivation is the following. Since we are studying some string, then we should say what to do with its end. And one natural thing to do is simply to fix on this end. So this is u, this is x. Uh, it means that a u of t and 0 equals to 0. So it's called directly a boundary condition. So another option is to leave this end of string free, which means that there is some pole here, and uh, mm, there is a ring sliding on this pole that is connected to our string. So this ring is massless, and so projection of a force onto this vertical axis should be zero, which means that so there is some F, some force, which means that x derivative of u should be zero. That ux of t and 0 equals to 0. It's called Neumann. And there is also the third option, which is interesting because it still has a good behavior, although it is not that easily solvable. So there is a mixed boundary condition. Uh, which corresponds which physically corresponds to a situation when we have some spring connected to this ring. So it is something like this. So this is called mixed, and it is written as alpha u of t and 0 plus beta ux of t and 0 equals to 0.
I've never seen that before. Can you describe a physical situation where you use a mixed boundary condition?
But I've just described it. It's a situation where we have some spring connected to this ring. Or do you mean some physical situation without such artificial constructions? Mm, uh, Actually, don't know. Probably we can invent something in electrostatical problems. Uh, but I think such boundary conditions appear rarely, so it's not something common. Mm. Okay, so we have 3 minutes, and let us try to solve one of these problems in this remaining 3 minutes. Uh, so again, we know that the solution of our equation is given by the sum of two functions, f of well, probably x plus t, x minus t. So there are initial conditions, but let us see what happens what happens with boundary condition. it tells that f of t plus g of minus t equals to 0. So, one equation, and we also have equations for f and g in terms of u0 and u1. So we know that fx uh, so this is valid for all positive t's. Maybe we can say for all t's. So one function is a reflection of another one. And we also have this equations that f of x uh, plus mm, let me think. Oh, maybe let's not solve this equation, but use some trick immediately. So this relation suggests us that there should be some relation between functions for positive and negative t. So this suggests the following trick. That is called method of reflections. So, the trick is the following. Uh, Let us study. So originally we had uh, u of 0 and x equals to u0 of x for x positive, and the same for ut. So let's extend them to the whole line. In the following way. Let us say that u0 of minus x equals to minus u0 of x. And u1 of minus x is minus u1 of x. So so we impose the symmetry of initial conditions, but we can also notice that our equation has the same symmetry. In a sense, if we take u of t and x solution, then u of t minus x is also a solution. Because second derivative, because first second derivative in minus x is the same as second derivative in x, and second we can simply look at its solution. If we change x into minus x, it's again a sum of these functions. So combining this, we see that a solution of equation of these initial conditions also has this symmetry. So u of t minus x equals u of t and x. So in particular, if so equals to minus u of t and x. In particular, if we put x equals to 0, this u will be 0. T 0 equals to 0. So solution of this equation with this extended initial conditions gives a solution to the equation with a zero boundary condition. So we'll continue with this next time. So thanks for your attention. So next time we meet in this room.